Welcome to Elementary Calculus, Chapter 2, Section 6, where we are talking about word problems, applications, specifically growth and decay problems, and we're going to mix in a little bit of the mathematics of finance. Finance is not my department. I've got you covered on the math, but if you have additional questions about some of the terminology in this section, please refer to a teacher or instructor or a professor in your department of business or finance perhaps. But on the math side of things, I got you. Let's have a look. Exponential growth and decay does not just apply in the field of business. For sure, it is utilized in biology and the social sciences. And the exponential growth and decay function, this is the Pert formula again. The y that's on the left-hand side of this equation is capital A. Y sub 0 on the right-hand side is indicating that that's a starting amount. A subscript of 0 is often used to indicate that it's a starting value. So that would be capital P in the Pert formula. And K is usually thought of as frequently as an interest rate or a rate of growth, or a rate of decay. And that's exactly what it is here. Your K value, if it's greater than 0, is a growth constant, and if K is less than 0, it's a decay constant or a rate of decay. And we're going to go in and look at more than a couple of word problems. Let's see what we've got. Example number 1. I was trying to slide the screen up and I was just drawing lines on the screen. Paul must make a balloon payment, which is like a final payment. Maybe you're paying down some debt, but they tell you that once you hit the 10-year mark, if you haven't paid it all off by then, you've got to pay off the entire remaining balance all at once, one final payment. And often that's called a balloon payment. Sometimes you're paying out that balloon payment. Sometimes that balloon payment, if you're fortunate, is coming to you. So he's got to make this balloon payment of $7,000 in 10 years. And we want to find the present value of the payment if it includes annual interest of 9% compounded continuously. All of a sudden I can't use my finger to scroll. Why is this happening? All right, so we've got the balloon payment of $7,000 is happening in 10 years. And remember that this version of the equation that we're looking at says y equals y sub 0 times e to the kt. And the final payment is $7,000. Find the present value. That would be our starting value, y sub 0. So we don't know what that is yet, but we're going to multiply it by e to the, our k value is going to be 9%, and we'll represent that as a decimal, so 0.09. And he's got to make that balloon payment in 10 years, so our t value as measured in years is going to be 10. And all we have to do is solve for y sub 0. I'm going to do this arithmetic in the exponent position. Which makes the new exponent 0.9. And then, because all I'm doing is solving for y sub 0, I don't need to use the natural log function at all here. All I have to do is get y sub 0 all alone. So we're going to divide both sides by e to the 0.9. I'll put a little note that says that that's what we're doing. And from there, I guess we could jot it down and then we'll go into the calculator. 7,000 divided by e to the 0.9 equals y sub 0. So far, this has been too easy. So why is it worth me practicing this? If anything, maybe it's worth practicing it just so that you can practice using your calculator. This one I'm going to do using my single line entry scientific calculator. Just in case some of you are using this arcane tool. And in order to type this in on this calculator, I'm going to type in, first I'm going to turn it on and clear it to 0. Okay, now we're ready. 7,000 is what I'm typing in, divided by, and then here's where it gets backwards. I'm going to type in 0.9. So far I've got 7,000 divided by 0.9. Then I'm going to hit the e to the x button, which means I have to use the second button, which is up here, and then I'll hit e to the x, which is over natural log. So I've got 0.9, I'm hitting second, and then the natural log button, so that it's e to the x. This, there it is, this value is e to the 0.9. This value has not been divided up into the 7,000 yet, but when I hit the equal sign on my calculator, it will do the division, and that looks correct because 7,000 divided by about 2.9 should be substantially less than 7,000, less than half of it, and I've got 2,845.987. And we're going to round to the nearest dollar, which gives us a final answer of $2,846. Not so bad. Being able to interpret the question, for sure, is something you might want to go back and revisit. Make sure that you're comfortable with where and why these different numbers went into the formula in the place that they did. Our next question is about effective rate. And this is where you could get a really thorough explanation from someone in a business department or in finance. So there are some key words in here, and again, you want to refer to your respective department so that you're interpreting questions given to you by your instructor correctly, or your professor. But there's a distinction that needs to be made between nominal or stated interest rate from what we call the effective interest rate when compounding is taken into account. So we're distinguishing nominal from effective. And to do this, we use what is called the effective rate for compound interest. So compound interest has, well, we know what compound interest is. Maybe quarterly you're receiving or paying out some portion of the interest for the year. But it's compounding, so you're paying interest on interest. What if you were to figure out a continuous interest rate that could be applied that would ultimately cause you to pay the same amount of interest by the time you got to the end of the year? You can see that there's a distinction that has to be made there. So that's the kind of distinction that we're talking about. Let's go in and look at this formula. This is the effective rate for compound interest. So R, we're being told, is the annual stated rate of interest. M, as usual, is the number of compoundings per year. And the effective rate of interest is this value on the left-hand side, R sub E. Great, now we know what all of our values represent. We know that the effective rate we're being told here is also sometimes referred to as the annual yield. So that's the final amount, it sounds like. And when interest is compounded continuously, we use the effective rate for continuous compounding. The effective rate for continuous compounding, okay? And the effective rate for continuous compounding is given to us here. E to the R, we'll calculate that, and then we'll do -1. All right, so let's make a little bit of sense out of this by applying it in example 2. We want to find the effective rate, which is R sub capital E, corresponding to a nominal rate of 6% compounded monthly. And we're rounding to the nearest hundredth. So we've got two scenarios that you can see on the screen. We've got effective rate for compound interest, and then we've got effective rate for continuous compound. Because example 2 tells us that we're compounding monthly, we know that we want to use this formula for calculating our effective rate. So let's do that. I'm going to copy it down into our problem so that I can scroll it off the screen. So R sub E equals 1 plus our rate divided by the number of compoundings raised to the power of the number of compoundings minus 1. And then we need to make sure we can find our values in the body of the question. So we've got a nominal rate of 6%. That's going to be our R value as a decimal. We're compounding monthly, which tells me that my M value is 12 compoundings per year. And those are the only two unknowns. So let's get them in there and get ourselves a final answer. Our effective rate is equal to 1 plus 0.06 divided by 12 raised to the power of 12 minus 1. I'm really exaggerating that 1 on the outside so that I don't forget it. I don't want it to just look like an accidental marking on my paper. And then I like to do a little bit of paper and pencil work to get this thing as ready for the calculator as possible. I'm trying to make it as simple to type into the calculator as possible, especially for you, because I don't know what kind of calculator you're using. So let's do a little arithmetic. Certainly, we can do 0.6 or 0.06 divided by 12. Let's just turn that into a decimal. We get 0.005, still being raised to the 12th, minus 1. We can add the 1, or sort of combine like terms on the inside of the parentheses there to get us 1.005. Raise that to the 12, subtract 1. Even on a scientific single line entry calculator, this one's really easy. We'll take the 1.005, we'll raise it to the power of, and remember, to raise it to the power, you need to use this Y to the X button right here, or sometimes this button looks like an upward facing arrow. There are probably some other ways of representing the exponent, but I'm going to hit that button and type in my 12 and hit enter, and then don't forget to hit minus 1 equals, and we have our effective rate. And it is, rounded to the nearest hundredth, 0.06. I got 0.06, and on my calculator it said 16778 and so on, but that's okay. We're rounding to the nearest hundredth. That's still R sub E, and that is our final answer. Either this is our final answer. Let's see, find the effective rate. Interesting. So this is 6% as a decimal. If we wanted to give this answer as a percentage, maybe we should take this decimal. I'm going to write it as 0, if my pencil will work, 0.061677. That's as a decimal. Then let's convert it to a percentage, which would be 6.1677%. And if we rounded that percentage to the hundredths place, our final answer would be rounded 6.17%. There's a distinct possibility that this is the answer that they're looking for, because it's just slightly different than the nominal rate of 6%. If the nominal rate and the effective rate ended up being identical, it wouldn't be a very good illustration. So my guess is that 6.17 is the answer they're looking for. And then let's talk about limited growth. Limited growth is, I've seen it represented as a logarithmic equation or as an exponential equation, And when you think about something growing exponentially, you can imagine this curve that goes swooping up maybe as a growth equation. Maybe it's cruising along the x-axis, and then it crosses the y-axis at 1, and then it goes curving rapidly up into the first quadrant. And that is an illustration of exponential growth. But if you're talking about population in particular, whether it's people or bacteria or whatever, there's often going to be a limiting factor. The amount of real estate available, natural resources, food, water, things like this, space. And so that kind of a limiting factor is what causes us to have a limited growth function. And in example number 3, we're being given an example of one of those. The sales of a new model of notebook computer are approximated by this function, where X represents the number of months the computer has been on the market, S represents sales in thousands of dollars. In how many months will the sales reach $2 million? What would be a limiting factor of the sales in thousands of dollars? Or if we were representing sales in number of units sold, what could be a limiting factor? Why can't I just sell infinitely many computers? Well, there's a bunch of limitations. Demand, for one, there aren't infinitely many people, so we don't need infinitely many laptop computers. There's the rate of manufacturing. There's shipping space to be taken into consideration. We could go on and talk about limiting factors. But all of those have been taken into account in order to, or some of them have been taken into account in order to create this equation that we're working with here. And let's get back on track. In how many months will the sales reach 2 million? So where does the 2 million go? Is it the X value or is it S of X? And the answer is it's the left-hand side of the equation, S of X, where S represents sales in thousands of dollars. So what number am I going to put into the left-hand side of the equation? Do I put in 2 million? Is that my S value? If S equals 4,000 minus 12,000 times e to the negative x over 10, and S, where did it go? S represents sales in thousands of dollars. How many thousands of dollars in sales did we have? Did we have $2,000,000? I think that would constitute 2 billion, but we've only got 2 million. So our S value is actually $2,000,000, which is equivalent to 2 million. Here's our 4,000 minus our 12,000, e to the negative x over 10. What would you like to do first in this equation? Just think about it for a second. If I gave you the pencil, what would you do next? You got some options. You could subtract 4,000 from both sides of this equation as we work toward isolating our x value. Something that I'm seeing, though, is that this term and this term and this term, they all have 3 zeros in them. I'm going to divide the entire equation by 1,000 just to make my number smaller so I can write less later. I'm not lazy, I'm efficient. You can borrow that line if you want. You're so lazy. I'm not lazy, I'm just being efficient. Doesn't that look like a much more manageable sized equation? I like these numbers better. It's way less intimidating anyway. Now let's subtract 4 from both sides as we whittle away at the right-hand side of this equation. Really, maybe the only challenge of the equation is knowing where to put which values. Maybe, depending on the instructor that you have, if you have to memorize this formula, this equation, or some particular equation that's given to you, maybe memorizing it's going to be the hard part. But from here on, the arithmetic should be pretty easy. So let's take away 4 from both sides so that we've got negative 2 on the left, negative 12e to the negative x over 10 on the right, and I will divide both sides by negative 12. Remember that our goal is absolutely to isolate that x value over there. Dividing by negative 12 and simplifying on the left-hand side gives us positive 1 over 6. That's dividing and simplifying. Right-hand side, e to the negative x over 10. Should I do it? I'm very tempted. Why not? Let's do it. Let's get mathematical on this thing. I'm going to raise both sides of my equation to the negative first power. What happens when you raise something to the negative first power? When there's a negative in the exponent, that negative is telling you to take the reciprocal. So what I'm doing here is I'm telling us to take the reciprocal of both sides of this equation. I'm going to write it all out. I've got 1 over 6 to the negative first power equals e to the negative x over 10 to the negative first power, right? I just put both sides of my equation to the negative first power. On the left-hand side, that exponent of negative 1 is telling me to take the reciprocal, so the left-hand side becomes 6. I love that. It's not a fraction anymore. Nobody likes fractions. That's not true. They're not all bad, but most people say that they don't like them. On the right-hand side, I'm going to use the power rule for exponents, which says that if I have a value to a power, I can multiply my powers together, my exponents. And a negative times a negative makes a positive, which means that the right-hand side of my equation now says e to the x over 10. Wasn't that a nice little trick? Did we have to do it that way? No. From this line right here, instead of raising both sides to the negative first power, could I have taken the natural log of both sides immediately? Absolutely. And, for that matter, I recommend that you try it. Try doing it that way and see if you get the same answer as I'm about to get. As a matter of fact, now I'm going to take the natural log of both sides. I'm doing it now to something that I think is nicer to work with instead of having done it earlier on these two things. Not so nice. All right, so we've got the natural log of 6 equals the natural log of e to the x over 10. I think we've covered this before. The natural log and the e kind of cancel each other out because the reverse power rule for logs says I can bring this down here and the natural log of e is equal to 1, so it goes away, leaving us just with x over 10. In order to isolate x, all we have to do is multiply both sides by 10, and we got ourselves an answer, an exact answer. So that's an exact answer. I'm a math guy, so I love that answer because it's as precise as you can possibly be. We're trying to find this x value rounded to the nearest month. So now I'm going to take this, plug it into my calculator, and round to the nearest month. In my scientific calculator, I will type, I'm going to do this from right to left. I'm going to hit 6, and then I'm going to hit the natural log button, which gives me automatically, I don't have to hit the equal sign, I get 1.791 blah blah blah. And then I'm going to do times 10 equals, and I get 17.91 blah blah blah. And again, we're supposed to be rounding to the nearest month, so we'll take this up to 18. And it'll take 18 months. Any other nuances that we need to talk about? It's going to take me 18 months to make $2 million in sales. That's not profit. It sounds more like revenue, but I'll take it. Additional applications. This is page 4, and in fact, Page 5 is blank, so this is our last example application problem. Let's see what we've got. Barbara knows that she will need to buy a new car in 2 years. That's a lot of forethought, Barbara. The car will cost $15,000 by then. Okay. How much should she invest now at 6% compounded quarterly so that she will have enough to buy a new car, rounded to the nearest cent? And then we're given the compound interest formula, which is very nice. Unfortunately, in 2 years, even compounding quarterly, I've never worked this problem out before, but I'd be willing to guess it's going to be pretty close to $15,000. Let's see. The capital A represents our final amount, so we know that she's going to need the $15,000 to buy the new car. What we don't know is her starting amount that she needs to invest, but we know that she's going to invest it at a interest rate of 6%, so as a decimal 0.06. We're going to divide that by 4 because she's compounding quarterly. And she's going to invest for 2 years, and the M value again is 4 for compounding quarterly. Oh, all we have to do is solve for P. Isn't that nice? And we're not going to need to take a natural log because we don't have any variables in the exponent position. This is an arithmetic problem. I love this problem. I'd rather that we knew how much she had available to invest and that we were having to figure out the amount of time she would have to wait until she had enough money to buy a car. But we got lucky on this one, this arithmetic problem. So 15,000 equals P times, let's go calculator. We don't want to mess up the arithmetic. I've got 0.06 divided by 4, and I got 0.015. So this is 0.015, and then I'm going to do plus 1, which equals 1.015. Let's not change everything. The exponent of 8, I think it's reasonable to do 2 times 4 in our head. And let's solve for P now. I don't really want to know what this decimal is. And I certainly don't want to write it down. So let's divide right away. Let's write down 15,000 divided by 1.015 to the 8th power, and that's going to give us a dollar figure for how much she should invest. All right, I'm going into my little scientific calculator here. 15,000 divided by 1.015, and then I'm going to hit the exponent button, which looks like y to the x, and then I'm going to hit 8, and then I'm going to hit equals, and I got $13,315.67. And we're supposed to be rounding to the nearest cent, and I just did. So let's jot down our final answer of $13,315.67. You think it's a good idea to take and lock up $13,315.67 for a couple of years in order to make about $1,700 so that you can afford to buy your new car? I think that's pretty responsible. I just wish I had $13,315 laying around. I would be willing to bet that you do too. That is the last problem for this section, and I appreciate you spending some time with me. I hope that working through those word problems was helpful to you, and I hope you'll visit me in another video. Thanks so much.